Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject CEC 334 Analog IC Design for 6th semester ECE students. In today's lecture, we will discuss the high frequency and noise characteristics of amplifier circuits with special focus on cascode amplifiers, differential amplifiers and statistical noise analysis. Understanding noise behavior is critical in analog and RF circuit design because noise directly affects signal quality, sensitivity and overall system performance. Why noise matters in high frequency amplifiers? Noise is an unavoidable phenomenon in electronic circuits. It determines how the minimum signal level that an amplifier can detect. In communication systems, radar systems and wireless receivers, weak signals must be amplified without significantly increasing noise. At high frequencies, device parasitics, short channel effects and transistor limitations increase noise contributions. Therefore, accurate noise modeling and optimization are essential to achieve a low noise figure and a high signal to noise ratio, commonly called SNR. Next we see about the cascode amplifier stage. The cascode amplifier combines a common source transistor with a common gate transistor. This arrangement provides several advantages. First, it achieves higher gain while maintaining wide bandwidth. Second, the common gate transistor suppresses the Miller effect by preventing large voltage variations at the drain of the common source device. As a result, bandwidth is significantly improved. Another advantage is better input-output isolation, which reduces unwanted feedback and minimizes noise coupling. Because of these benefits, cascode amplifiers are widely used in RF amplifiers and integrated circuit design. Next we see about the noise sources in cascode amplifiers. Several noise sources affect cascode amplifiers. Thermal noise is generated by resistive elements and transistor channels. It has a flat frequency spectrum and is often called white noise. Flicker noise, also known as 1 over F noise, dominates at low frequencies and is caused by charge trapping at the silicon dioxide interface. Short channel MOSFETs introduce excess noise due to velocity saturation and hot electron effects. Another source is substrate-induced noise, where noise couples through the semiconductor substrate into the active device. To design low noise amplifiers, engineers must carefully model and minimize all these noise sources. Next we see about the differential amplifier stage, noise and frequency traits. Differential amplifiers provide significant advantages in noise performance. One major benefit is common mode rejection. Any noise appearing equally on both inputs is largely cancelled at the output. Noise generated by the two transistors is statistically independent, therefore, the total noise combines using the root sum square method. Differential method amplifiers also reject even order distortion and offer excellent immunity against power supply and substrate noise. However, transistor mismatches can reduce common mode rejection ratio, especially at high frequencies. This is why careful layout techniques such as common centroid placement and interdigitated structures are widely used. Next we see about the statistical characteristics of noise in MOSFETs. Noise is fundamentally random and must be analyzed statistically. Instead of describing noise using a single value, engineers use power spectral density or PSD, which shows how noise power is distributed across frequency. The thermal noise exhibits a flat PSD and is therefore called white noise. Flicker noise follows a 1 over f relationship, meaning its magnitude increases as frequency decreases. To compare amplifier performance, parameters such as noise figure, minimum noise figure, and equivalent noise resistance are used. These parameters help designers select suitable devices and optimize amplifier performance. Next we see about the high frequency noise modeling. Modern amplifier design requires accurate noise modeling. Simple analytical equations are often insufficient for advanced CMOS technologies. Therefore, designers use physics-based simulation tools and compact transistor models such as BSIM4 and PSP. These models account for channel noise, gate resistance noise, and the correlation between different noise sources. Simulation results provide important design parameters such as minimum noise figure, equivalent noise resistance, and optimum source impedance. These values are particularly important when designing low noise amplifiers for RF applications. Next we see about the case study of 800 MHz CMOS low noise amplifier. This slide presents a practical example of a CMOS low noise amplifier operating at 800 MHz. The amplifier achieved a noise figure of only 0.9 decibels, which is excellent for CMOS technology. The circuit operates with a bias current of approximately 3.75 milliamperes, demonstrating low power operation. Through proper transistor sizing and source degeneration techniques, the design approaches the theoretical minimum noise figure. Statistical noise analysis confirms predictable performance across the operating frequency range. Next we see about the noise spectral density with the frequency profile. This graph illustrates the typical noise spectrum of a MOSFET amplifier. At low frequencies, flicker noise dominates, causing the low noise to increase significantly. As frequency increases, the thermal noise becomes dominant, creating a relatively flat noise spectrum known as white noise. The transition point between these two regions is called the 1 over f corner frequency. The total RMS noise within a system depends on the area under the noise spectral density curve over the desired bandwidth. Finally, we came to the summary and the design takeaways. Let us summarize today's lecture. Cascode amplifiers provide high gain, wide bandwidth, and reduced Miller effect. Differential amplifiers offer excellent common mode noise rejection and improved immunity to interference. MOSFET noise originates from multiple mechanisms including thermal noise, flicker noise, short channel effects, and substrate coupling. Statistical noise parameters such as noise figure, minimum noise figure, and equivalent noise resistance are essential for evaluating amplifier performance. Finally, accurate device modeling and simulation enable engineers to design efficient low noise amplifiers and RF front-end circuits with high confidence. Hope you all understood. We will see in the next lecture.